say the 1, you do that. You go,
Yeah, you
remember
go.
life, it's accident. Okay, Earth science time. Please write this down in your notes. We're going to discuss today. I want to think of a cool and cute title for this, but I'm trying to think of how to date Earth. This is a cute title. Question mark? Heart? It's actually just the letter B. How to date Earth. So there's some concessions made in this title. Kesson, would you hop over there and make sure the mic is picking up? There's a little mic bar on the bottom, and it should be filling up and going down as my voice speak. Is it doing it? Okay, thank you. How to date Earth. Let's put in XOXO. Yeah. So there's a joke here. Obviously, you, since you're hormonal little teenagers, think that the first instinct is that I'm talking about going on a date with someone thick named Earth, but that is not what we're talking about. What's another way that we might use this word date as a verb, specifically in earth science and not in Arby's? Yeah, we're telling how, I'm going to give you a sentence frame, telling how something is.
Oh.
Yeah. Something is with it.
Telling how much understands.
So, telling how old something is. Remember, Gunnar, the microphone does pick up your voice, so please don't say things. Telling how old something, you can say things. This is a discussion, but I don't want you to just throw in your weird words that I don't know the definition of, and so it's going to get me in trouble. Telling how old something is. We're going to talk about 3 things. This has 3 parts, and we're going to list them here, and then I'm going to immediately erase them, and we're going to move on to talk about the first one. But I'm going to make you tell them to me. What are 3 very broad categories of the way we might be able to tell how old Earth as a planet or the objects there within or even the universe in general is? Let's hear one. Okay, I'm going to put that as number 2. What about the rock layers? We're going to do, let's put rock record. Let's put that. The rock record. You know, when I talk about record, I'm not just talking about vinyl records. I'm talking about recordings thereof. But it's not recordings like we're making right now of this discussion. It's recordings from all of Earth's history in the rocks themselves. That's the rock record. What's another one? I know what you're talking about, and I want you to, not radiology, that ain't quite right, but we're using radiometric dating. So this is like when you find out that the chick you went to Arby's with has a radio. What a stupid thing to say. Yeah, it's radioactive like Superman. She got the dadgum kryptonite. I don't know what I'm talking about. What's the first one though? What's the main way? Especially, I'm going to give you this hint. Yes, I was going to give you a hint, but you don't need it. Fossils. Fossils.
Fossil.
Whose lab was about fossils? Raise your hand. Good. Whose lab was about the rock record? Yeah, I would say yours is too, Haley. Whose lab was about radiometric dating? No, this one's kind of tricky to do in the lab. The main lab that we sometimes do for that one is like everyone flips pennies, and that represents half-life, because half-life is how long it takes for 50% of the isotope to decay. We'll talk about that later. And the pennies have a 50-50 shot of being heads or tails. What's up?
I was going to do that lab, but it was too.
Below grade level. Right. Okay, so we'll talk about the rock record and radiometric. Someone remember how I phrased these two, because we kind of made that up, and I'm just going to erase those, and we'll come back to them. So first we're talking about fossils. What a fossil is? You know the answer to this. What a fossil is.
Rock.
That's not a bad answer, Justice. Is every rock a fossil? No, so obviously that's not the best answer, but it's better than you think it is, because a lot of people, we might even say idiots, think that a fossil is a bone. Like that when you go, as we're going to go to the museum, that you are seeing the bones. Usually that's not the case. It's actually much truer to say that a fossil is a rock, as Justice did. That's not always the case. Yeah, okay, so petrified, we'll talk about that in a second, but petrified means made into, no.
Mineral preserved.
Yeah, minerals, it's preserved, but it's made into rock, we might say. It is made into minerals, yes. What's up? Okay, so an ancient, we might say, and we're going to specify that, but ancient And it's not just, and I will say that a lot of times, yeah, and plants, and even more than that, anything that was ever alive, ancient life. And it's not all ancient life, and it's not only ancient life, it is the evidence of ancient life. How old is ancient? There is a kind of general rule of thumb that we use. It must be greater than how old? Can you guess?
100.
Much older than that.
Oh,
Million, not quite a million. Almost, Justice.
7,500.
10,000 is usually what we agree upon. 10,000 years. Let's talk about this now. Another way to express this is 10 kilo annum. You remember these? You remember these from 8th grade science? You should. Let's have a little box right here of these units of geologic time. We use these a lot. Lowercase k, capital A equals kilo annum. How many years is that? 1,000 years. What about capital M, capital A? You remember? You're right, Ty, but what's its name? Do you remember? Mega annum. 1 million years. And then the other one, or the largest one, is, do you remember? You're right, Ty, but what's its name? Giga. You got it. Thank you, Hunter. Giga annum. 1 billion years.
I know you just spit all over that.
Yeah, the mic picked up. The mic's like, you listen to the video later, there's just like, it's like a firework going on. So we have these units. You should probably have those memorized. They will come up. I think if I'm right, they're on this test kind of in this form, like which one means what. But we'll continue to use them as we talk about geologic time for the next 2 units also. So we have fossils as the evidence of ancient life. And then we mean greater than 10,000 years old when we talk about that. What does it mean for something to be alive? What is the definition we agree upon for a living thing? Remind me from biology. It doesn't have to breathe.
Water-based.
That's not one of the definitions. Cellular. Cellular. What else is true of life? It must always, doesn't always, but it must be able to. No, not breathe.
Reproduce.
Reproduce. What's the other one? It must be able to. Kind of like this one, but it's within itself.
Survive.
Grow. Well, there's another one too. I don't actually remember what the other one is, so don't tell Mr. O. What is? Does anyone remember? There is another one. These ones are the important ones. There are 3 important ones. It must be cellular, it must reproduce, and it must grow. There might even be 5. I'm going to talk about those 3. So is a tree a living thing? Yeah. It is cellular. It's made of cells. It reproduces and it grows. Is a crystal a living thing?
Yeah, no.
It does grow. Crystals do grow. Do they reproduce? In a sense, sometimes crystals can grow out of other crystals. Are they cellular? No, they're not cellular. They're not. We, for some reason, and I truly mean that, I don't know the reason, but we agree as when we talk about biology that life must be made of cells. Sure it is. Crystals do have unit cells, but they're not cells as we normally define biological cells. What's up? Giga annum. Giga annum. What are some ways that fossils can form? Well, first let me ask you this question. Does everything that dies fossilize? Hey, remember, that's the other side of life is death. Everything that has ever lived must someday die. And in order for there to be life, there must be death. You know you are alive, but you are made out of dead stuff. What did you have for breakfast, Gunnar? Dead stuff. But what was it specifically? Was the egg alive when you ate it? No, that would be spooky. Don't do that. What else did you eat? What else did you eat?
Sausage was in there.
Sausage was in there. Was that made of dead? Yep, that's a gross way to think about it. While you're eating a sausage, don't think I'm eating a corpse, but you are. What else? Gravy, which was made of, gravy, I'll tell you, is made of milk, flour, and those are animal things. It's also made of salt. Is salt living? No, but that we don't really eat salt as such. Like, that's not your main food. Milk is made from a thing that grows. Yeah, it's a byproduct. So all life comes from death, and all living things must die, but do all dead things fossilize is the question. No, Hunter.
There has to be like a rare event.
Yeah, only few living things, dead things, fossilize. The example I often give, who's a hunter? Who hunts? I bet you do, Dalton. I'm going to use Ty as an example, though. So Ty, great hunter Ty, as Nimrod from the Bible, Ty has his rifle, and he sees a coyote running across the field at Anders Field, which I can see from here, I think. So there's a coyote out there, and Ty's dad says, "Well, boy, you better get your gun and shoot that coyote." And so what does Ty do? Ty gets his gun and shoots that coyote. And I don't know how things run at the Anders house, but I can imagine that there are some people around who shoot a coyote and then it just sits. You know, like the pelt is worth almost nothing as I understand it nowadays. And so it just sits in the field. If you came back, nothing happens to it. You don't touch it. Even assume like your livestock or other scavengers, like macro scale scavengers, don't touch it. If you come back in 1 year, what will be left of it?
Bones.
No. Wrong. Almost certainly not. There won't even be bones. Dust. It still exists. I'm not saying the matter has vanished, but it is dust. It's dispersed. There will be nothing left. Can bones exist for a long time? One time I taught this to Ty's sister, Dally, and she said, "Well, that's not true, Mr. Kime, because we have basically a carcass pit for your dead cattle, and the bones from years ago are still there. They're just in a pile." Are there any that are 100 years old? Probably not. Are there any that are 1,000 years old? Are there some that are 10,000 years old? So no, even those ones, even if you have a problem with me saying that a year there may still be bones, you understand that probably in 10,000 years there probably won't be bones, because only few dead things fossilize. I'm going to give you an estimate, maybe less than 1% of things fossilize. That's not a strict rule. It's not like 1 out of every 100 things on the dot fossilizes, but I'm going to estimate that less than about 1% fossilize. Why? Hunter, what do you think?
Because there has to be like an event like sediment covering it up or a flood where...
Sediment covering. Give me a vocab word. Oops, sorry. I don't know if it actually is a vocab word, but give me a word that means sediment covering.
Sedimentation.
Burial. Yeah, it usually has to be buried. What's up?
For Hudson Mango, they didn't just...
No, they didn't. Why? Probably because they were buried. And it has to be. It usually has to be rapid. Like soon after that, because remember, and when I say rapid, it doesn't have to be like within 30 seconds, but probably within about a year. Otherwise, things are going to start. Big things and small things are going to start taking it apart and using that resource. Remember, life comes from death, and so a dead thing dies. The living thing's gonna be like, yum, sausage. Let me at my breakfast. I was riding. Blue jay out there. I was riding my bike last night on the trail, and I was like, that's a weird, spooky looking bundle of sticks. But it wasn't a bundle of sticks. It was the front leg of a coyote, with its like radius and ulna and its little paws all held together by some mummified, tattered flesh. And I was like, that is a spooky stick. But I'm going to tell you the dang truth. When I go back on that trail today, it won't be there. What will have happened to it? So maybe a witch snuck out of the woods and took it. But let me tell you, that still counts. But probably another coyote or even something like a squirrel or a deer will eat bones because they need calcium in their diet, and things eat bones. An animal will have eaten it. Maybe even a hawk will come down and pick the meat off of it. I mean, there's all kinds of things, all kinds of life. If something dies, living things come from all over to ingest that. So it has to be buried to protect it from large things, usually, and needs to be rapid, and it's usually a wet environment. It usually involves some kind of water. And that's kind of a double-edged sword because the water can also degrade the biological organism. But if all these things come together, we end up with some of these methods of fossil preservation. Methods of preservation. The main ones that we talk about are cast and mold, permineralization, which we also call petrification, carbon film, and I'm just going to put OG for the last one, and we'll talk about that.
Original gangster.
Yeah, original gangster. A cast in a mold. If whose lab was it? In your lab, Ranchan's, you had a piece of clay, and you pressed something into it, right? And then you took the thing out, and what was left was a negative image. Right? Everywhere where there was a hole, there was a little mound. Everywhere there was a mound, there's a little hole. You're left with a negative image of the thing you press into it, right? That's called a mold. I think your book is wrong. It is. On page 561 of your book, I'll show you on the camera. I did a terrible job of this last time, though, so I'll try to show you on the camera. This little picture here says... I probably did bad. This little picture says that a cast is on the left and a mold is on the right, but it's actually the wrong way around. That caption is just wrong. A mold is a negative impression. A mold is a hole left when something's pressed in. And then sometimes, like your plaster, does everyone know what I'm talking about when I'm talking about their lab? They pressed things into clay and they covered that hole with plaster. And then when the plaster dried, they took it out, and that had the same shape as the original thing. So is that original thing still there? Like when it was the Hot Wheels car, is it still an original Hot Wheels car when you take it out? No, now it's made of plaster. So it's different stuff from before. And recognize that even if the thing now decays, right, gets pressed in, even if it decays, that hole is still there. Because things ate the coyote leg or whatever, but they're not going to eat the hole left behind in the dirt. And then that hole gets filled in and that becomes a cast. We'll talk about that in a second, but do remind me because I almost forgot those. So I hope you wrote something down for that. I'm just describing these out loud. I wrote down their names, but I'm just talking about them out loud. Permineralization is almost the same thing, or it's similar, but it's on a microscopic scale. So you'll recognize that a lot of you is made of pores. You've got pores. Some of you have pores on your nose that I can see. But even your bones have pores in them. Everyone has holes all over them, right? A bone is a porous thing. And so maybe that coyote that Ty shot dies. And as it's buried, the holes, the bones will still get eaten or whatever, but maybe those holes get filled in with mud, and then even after the bone is gone, the mud is still in the shape of a bone. This is the one that is the most, it's not the most common fossil preservation, but it's the most common for ancient fossils. So like dinosaur fossils that we find, which are very, very old, or even older than that, trilobite fossils from 300 million years ago are often because of petrification, because the little holes in the organism got filled in with rock, and so now it's a rock, right? It's not an organism, it's a rock shaped like an organism. That's petrification. Carbon film happens a lot to leaves and fish and other flat things where they just get squooshed and their fluids come out, and those fluids get decayed into just carbon. And so it's almost like a pencil mark that's in the shape of that organism. And then OG is the original. It can be either hard or soft parts. But why is this one so uncommon, do you think? Like this would be an actual bone or an actual eyeball. Why is this one so uncommon? Yeah, because it gets decayed. Right? If that coyote, if this is a hypothetical, but if Ty shot that coyote now, probably by tonight it wouldn't have eyes anymore. Birds would have come and eaten its eyes. Probably by tomorrow it wouldn't have a liver anymore. Those are like the soft parts are going to be gone in very little time. So that's very, very, very rare. Can you think of an example where we would find the original soft parts, Hunter? What is it? In the resin, which we call, when it's solidified, we call it amber. You're thinking of, yeah, it's amber. You're thinking of Jurassic Park, and that is one of the only ways. That and tar pits and freezing are some of the only ways we find original soft parts or original hard parts, because usually things just decay. Now, Hunter correctly points out that in addition to these methods of fossil preservation, there are also categories of fossils called trace and body. Sometimes we call trace indirect, and sometimes we call body direct fossils. But these trace fossils tell us about the behaviors. What would be an example of a behavior preserved? As opposed to the actual parts. So like a bone would be a body fossil. It's an actual part of the organism. But how would a behavior be preserved?
Maybe.
Give me an example. Let's start with an example.
Their poop.
Yep, exactly right. Poop, coprolite. We call it a coprolite when it's fossilized poop. What else? What else is not an actual part of the organism, but tells us about it? A feather is a part of an organism, but
The food that's
claw marks, good. Claw marks. Burrows, yeah, sometimes we find food, very rarely, but maybe a food in a, where might we find some little baby organisms? In a nest or a burrow, yeah. So things that are fossilized evidence of their behavior are called trace or indirect fossils, and then the actual parts of them are called body or direct fossils. How much time do we have left?
No.
Are you serious?
No, we have.
We have 9 minutes.
Okay. So do you have questions about fossils in general? That was an extremely quick rundown of fossils, but do you have questions about this? Okay. Hearing none, let's move on. Whoa. Let's move on to part 2. I asked someone to memorize or maybe write down what the next part was because I've already forgotten. What was part 2?
Rock record on that.
Rock record, okay. The rock record. And I'm going to subtitle this Relative Age Dating. And the joke I love to make is that this is like when you see a cute girl at your family reunion. That's no, that's not true, Carson. Don't do that. The rock record, we call it relative age dating because we are when things are relative to each other, we're comparing them. So like your relatives are related to you. That is an etymological thing that makes sense to you. And in the same way that we might describe your position relative to this wall, right? Gunner is 2 meters north of this wall, right? Relative to this wall. So compared to this wall. So relative age dating is when we compare ages. We don't say things, relative age dating is not Justice is 17 years old. It is Justice is older than Gunner, right? So it's not numerical ages. We're comparing ages. We use terms like older or younger than. Or we might say earlier or more recent. Those are the terms we use for relative age dating. And does anyone remember from 8th grade science or maybe from your lab the most basic principle of relative age dating? I'll give you a sentence frame. The oldest things are on the bottom. Exactly right. This one is called the law of superposition. Very good, Hunter. Ramrock. Superposition. Oldest things on the bottom. Sometimes we specify in an unoverturned sequence because things can get turned over, right? The classic example, or the example I use a lot, is your nasty laundry pile in your room. Where are you going to find the oldest chonies? The bottom, right? Because you just made a pile. But what if your mom comes in and flips the whole thing over? Well, now the oldest ones are on the top, and there's a terrible odor in the room. But generally that doesn't happen. It takes some energy to overturn the sequence. And so in an unoverturned sequence, if it hasn't been turned over, the oldest things are on the bottom. If you're making a 3-layer cake, like Carson's mom, which one do you have to put down first?
The big one.
The bottom one. The one that has to go first is on the bottom. It would be crazy, unless you're making an upside down cake, but that takes energy, to put the oldest one on top. That doesn't even make sense. Another principle of relative age dating is that of original horizontality. Guess. When rocks are originally laid down, guess how they're laid down? Horizontally. So if we see rocks that are at an angle, we understand that angling happened after the rocks were laid down. Another one is lateral continuity. If we see a layer of rocks, we see multiple layers of rocks like this with a river cutting through them, would it be reasonable to assume that they laid down in this, like they stopped here? They just stopped laying down? No, they were continuous at first, but later a river cut through them. And finally, inclusions. Things that are included in a rock, like bits of other rock, have to be older than the rock itself. What might this be a picture of? It could be the moon. It isn't.
It's cheese.
It could be cheese. It's not. It could be anything because it's a circle with chunks in it. I was thinking chocolate chip cookie. The chocolate chip cookies have to exist before they can be in a chocolate chip cookie. Did I say that wrong? Chocolate chips themselves, the chocolate chips themselves have to exist before they can be in a chocolate chip cookie. So the chocolate chips are older than a chocolate chip cookie.
Yeah.
Trying to think about Takis. Like if you make a Taki cookie instead of chocolate chip cookie, like just a chocolate chip cookie, but you put Takis in it instead, you had to have the Takis first. They had to exist before that. And we use all these things together to tell which rocks are older than other rocks. But that doesn't tell us how old rocks are in general. And for that we use, what's the next one? That was 2. Radiometric dating. So let's erase all this. Hopefully you got that down. If you didn't, you can get it from the YouTube channel, but we are running out of time. So the last one that we're going to talk about today, or the last thing we're talking about today, is radiometric dating.
Because there's only 3. There's not 5.
There's only 3 things that we talked about today. Using what to tell the age of rock? Not usually. Someone said, I won't even say their name, but someone said carbon dating. And let me tell you, that is very useful in archaeology because the half-life of carbon-14 is about 5,000 years. It's not usually useful in paleontology. Let me tell you the difference between those. Archaeology is a study of ancient humans. Paleontology is a study of ancient life. Usually paleontology is dealing with things 10 or hundreds or thousands of times older than human beings in general. We use carbon dating a lot in archaeology because its half-life is 5,000 years, so we can say, well, this thing has had 2 half-lives of carbon-14, and so we can tell that this, maybe temple or whatever is 10,000 years old. But if we're talking about ancient life and we wanted to say something like, this is 250 million years old, carbon-14 is no longer useful.
Is that when we use Aaron and daughter isotopes?
Yeah, we do that with carbon-14 dating too, but it's just that we don't use that specific isotope for paleontology very much, using isotopes to tell the age of a rock. So these are decaying atoms, basically, and they have a known half-life. Basically, a certain amount, we abbreviate this with the Greek letter lambda, a certain amount goes away every certain amount of time. A certain amount, I don't know, I'm going to put changes over time. And we can tell that amount in a lab. We can say this element is emitting radioactive daughter products at a rate of whatever. And so that tells us that it takes this long for half of it to decay. We can see that in a lab. It's something we can actually physically observe. And we use things like zirconium or potassium isotopes. Strontium is used. And we look inside of a rock using mineral microscopes or bubble chambers or whatever. I actually don't, spectroscopes. Using an instrument of science, we can see in the rock that this much of it is the daughter and this much of it is the parent. And using that information, we can tell how old it is to within usually 1 or 2 half-lives. And so then that might mean a lot of difference for some things, but it gives us a pretty narrow range for others. And so we can tell pretty definitively how old something is. And using that in conjunction with the relative age dating we talked about, we can say, well, this fossil is 270 million years old, and the ones above it, for instance, might be 230 million years old, like Halley's project. Bye!